Swayam Prabha. Digital India. Educated India.
Welcome back, students. From the previous lecture, we started doing transistor amplifiers, BJT or MOS, with one transistor at a time. The first amplifier design we did was a common emitter or common source amplifier. Now we're going to do different variations of a single transistor amplifier, both for BJT as well as MOSFET. One thing I'm noticing, how are you using these video lectures is really important. What I'm observing is most likely you're just watching the video lecture and you think that you got it. My suggestion to you would be pause the video lectures. At every point I'm asking you to pause the lectures and then do the analysis. Try to do the analysis by yourself. The way we have organized the material is in such a way that you don't need anything new, any information to do those equations and analysis. So I have already taught you all those things. So you just have to go through the grind of the analysis by yourself. Don't just observe or watch what I am showing you on the screen, because you may perceive that you're getting all the information and you're getting the practice. However, I would strongly urge you to write down on a piece of paper and go through the analysis by yourself. So whenever I tell you to pause the video, please do the analysis by yourself or draw the schematic by yourself. And this is the only way you can get practice, so that when you see a new circuit in front of you, you don't get totally fumbled up. Okay? So follow that advice. Now in this lecture, we are going to start with common base amplifier and then follow up with a common gate amplifier for MOSFET case. We will look at the input-output characteristics, the gain, input resistance, output resistance. So in the beginning, it will feel like we are going through very slowly through each amplifier, making lots of approximations. But once we finish all three combinations of the amplifiers, then we will start putting together our own simple rule of thumb so that we can use them again and again whenever we do complex amplifier circuits. It's important that you understand single transistors amplifier very well. Then you can do complex amplifier circuits very easily. When we talked about common emitter or common source amplifier, it was the emitter or the source terminal which was common between input and output. Today's lecture, we will start with common base amplifier. As the name suggests, the base terminal will be common between input and output. What this means is that the input is applied between, in this particular case, between emitter and base, and output is looked at between collector and base. Let me draw the schematic first and then explain it to you. First of all, the base is connected to DC bias voltage source, V bias, over here, and input is applied between emitter and base over here, and the output is looked at between collector and base. Since we are applying a constant bias voltage over here, that node can be looked at as AC ground. Let's do small signal analysis for this, this particular schematic of common base amplifier. What we will do is VCC terminal will be grounded, also V bias terminal will be grounded. Okay, and a small signal model with the transistor should look like this for AC analysis. Vin is applied over here and Vout is at the collector. From this, we can go to a detailed small signal model. In this particular case, we will ignore the Rout of the bipolar transistor Q1 and do a first cut small signal analysis. So this is the base input resistance, R pi, and there is a V pi potential developed across that resistance, which will give us GM V pi from collector to emitter, and we are applying the AC voltage source Vin over here, right here, and the load resistor RL, which was over here, is shown over here, and this ground is representing our VCC because we are doing AC analysis. At this point, I would like you to pause the video and do the KCL KVL equations for this particular circuit and tell me what is the gain from input node to the output node. So what we are looking for is Vout divided by Vin. Okay, so let me explain how I got this. First of all, you can see the relationship between Vin and Vpi. Vpi is equal to minus Vin, and the output voltage Vout is given by Gm Vpi flowing through the resistor RL. That would give us this particular equation, and then we can substitute Vpi from this equation over here, and that should give us Vout divided by Vin is equal to Gm RL. One thing to notice here is this is a non-inverting configuration. In the case of common emitter amplifier, we had minus Gm times RL. In this case, we have Gm times RL. So there is no inversion when we go from emitter to collector in terms of signal flow. The next question that I'm going to ask you to figure out for this particular amplifier is what is the input resistance looking into this particular node, which is at the emitter of Q1. We would like to figure out what is the Rin for this particular configuration. Again, you can do the same analysis. Try to figure out what is In, and Vin divided by In should give you the Rin value. Hopefully you got the same answer. Let me explain the answer again. If you look at the total current In at this side over here, what is the In over here? That In is going to be equal to the current which is going to flow through the Rpi resistor and the current flowing this way. So the total is going to be Vin divided by Rpi, and due to the current direction it should be minus Gm Vpi. If you solve this, you're going to get Rin is equal to Vin divided by In, which will be 1 divided by Gm plus 1 over Rpi. Now Rpi is given by beta over Gm. So you can see here Gm plus Gm divided by beta. Since beta is large, we can ignore this quantity safely, giving us Rin value, which is 1 divided by Gm. Now so far what we have seen is generally reciprocal of Gm is a small value as compared to the output resistance. And if you remember from the previous lecture, we always wanted input resistance looking into an amplifier to be as high as possible. That is generally the case in most of the applications. However, in high frequency application, you need a very well defined or a fixed input resistance for matching purposes. So using Gm, what we can do is we can accurately control the input resistance by controlling the current flowing into the transistor. So this is very useful when it comes to high frequency circuit design. And there you need a fixed value of the input resistance. You may have heard 50 ohm termination or 75 ohm termination depending upon if you're dealing with cable or wireless antennas. That's what this resistance we are talking about. So in those designs where we are delivering power from the antenna to the input of your amplifier, we would like to have a very good matching so that maximum input signal power is transferred to the amplifier. We don't need to get into that right now. I just wanted to highlight that there are some specific applications where we would like to have input resistance which is small but fixed and controlled, very well controlled. And this is the example where if you need a 50 ohm termination looking into an amplifier, then we can use this particular amplifier. The output resistance of this particular amplifier is going to look like, again, over here it's RL, assuming Rout is very large. Similar analysis like what you would do in common emitter case. Now let's look at common gate amplifier. We just did common base amplifier. Now we are going to look at common gate amplifier. As the name suggests, gate will be the common terminal between input and output. Let me draw the schematic. We can do exact same analysis that we did for the bipolar case over here. Please draw the schematic for AC analysis. And the detailed small signal analysis, we can substitute the model for the MOSFET. You can easily prove it to yourself now that Vout, the gain of this amplifier, Vout divided by Vin, it's going to be equal to Gm times RL. Again, this is a non-inverting gain. You can also prove, similar to bipolar case, input resistance, which is resistance looking into this source node over here or over here, that is going to be equal to 1 divided by Gm. Again, we have ignored the Rout of the transistor. So applying input, sinusoidal input at the source or the emitter can be a little bit confusing in the beginning. So let me show you a common gate amplifier with some biasing structure. So you will understand how do you implement this circuit in practice. Pay close attention to the way I am drawing the circuit. I would recommend you draw that schematic in your book as well. First thing is we need to connect the gate to a bias potential. In this particular case, we can simply use a resistive divider. Since I have not taught you yet current mirrors, we are going to use a resistive divider first here. So this is R1, R2, and that should give us V bias potential at the gate of our transistor M1. We need to apply the AC signal coming from the previous stage, which is Vin, with a source resistance to the source of M1. So what we would do, as I have explained earlier, is we would use a big capacitor, C large, or also called a C block. So C blocking capacitor would block the DC and only lets go of AC signal through it at the frequency of interest, and RS is the source resistance here. As I said again, these resistors are used just for illustration purposes. In actual design, we would use transistors so that we get consistent performance over process temperature variation. In this case, how do you quickly figure out voltage gain of this circuit? Just by inspection. So here is a trick I'm going to show you. Let's call this source node as V dash. We know that gain from V dash to V out is given by Gm times RL. We just did that analysis few minutes ago. Now we need to figure out what is the transfer function from V in to V dash. For the AC analysis, for frequencies of interest, we are going to look at this blocking capacitor and we are going to say that it's a short. So what we would see then is we would see a circuit that looks like this. So you have V in coming in and you have resistor RS. Capacitor is shorted. We have R3, and along with that, for AC purposes, we have the resistance looking in to the source of the device. And we said from the previous analysis that this was 1 divided by Gm of the transistor. And this would be our V dash potential. So if you look at this circuit, you can quickly tell that V dash is nothing but a voltage divider between RS and parallel combination of R3 and 1 over Gm. So you can say V dash divided by V in is equal to R3 parallel combination of 1 over Gm divided by RS plus R3 parallel combination of 1 over Gm. We can extend this to gain by simply putting V out over here, V out, and then that would get multiplied by Gm times RL. So this is a quick way to analyze the circuit. So far we have done common emitter, common base amplifier. So now we have one more configuration left as the basic configuration for transistor amplifier, single transistor amplifier. And as you would have guessed it, it should be called common collector amplifier. So in case of common collector, we would have collector connected to some DC bias, and input is applied to gate and output is looked at the emitter of the device. So let's draw the schematic first. So you can see that collector is connected to VCC, which becomes AC ground, and input is applied to base of Q1, and output we are looking at the emitter. I bias is the constant current source that is used to bias transistor Q1. You can use a resistor, but for purpose of simplicity we are showing here constant current source. Now from this you can go to AC analysis, simple model. That's going to look like. From AC point of view, we would connect this particular collector to ground over here, and the constant current source I bias becomes an open circuit, and hence we don't have anything connected over here. Let's do small signal analysis with details of the transistor here. What I would like you to do now is figure out the gain, which is V out divided by V in. I hope you got the same equation. Now what does this equation really mean? V in minus V out multiplied by reciprocal of R pi plus Gm equal to 0. If you look at this term in the bracket, this cannot be 0. Hence V in minus V out has to be 0, which should give you V out is equal to V in. So the output voltage V out is following the input voltage, and this particular circuit gives you unity gain. So you get unity gain. This is unity gain amplifier, also called as a emitter follower. Pay attention to the nomenclature, emitter follower. So the output simply follows the input. Let's look at the input output resistance characteristics of emitter follower amplifier. So you can see first of all R in of this amplifier is going to be infinite, because the bias current I bias looks like a open circuit for AC point of view. Let's try to figure out what is the output resistance looking back in here, R out, and then you will understand the importance of this particular amplifier. So first I would like you to pause the video and attempt on your own, if you can, draw the small signal model of the transistor for measurement of R out. Remember, when you are measuring R out, or when you are trying to figure out R out, all the independent voltage sources, for example V in, you would connect them to 0, or you would ground them, you would zero them out. So you can write the equation IT is equal to minus V pi divided by R pi, that would be the current flowing in this direction, minus Gm V pi. And we know that V pi is equal to minus Vt. IT is equal to VT divided by R pi plus GM VT. So this should give you VT divided by IT, which is our R out calculation. That should be equal to, again, reciprocal of 1 divided by R pi plus GM. And we already know the approximation for this is 1 divided by GM. So in this case, we get R out, which is equivalent of reciprocal of the transconductance of the amplifier. So R out of emitter follower is equal to 1 divided by GM. Again, GM is large value, so R out is a small value. So we get a low resistance for R out by doing this. As we said earlier, we can control the GM by controlling the current. So if you really want ultra low output resistance, then you can increase the current, bias current in the transistor. And we know that GM is given by I divided by VT. So if you increase the current I, VT being 26 millivolts, we can increase the value of GM and hence reduce the value of output resistance. So where do you really need this kind of circuit? Because in this particular circuit, as I said, even though we call it common collector amplifier, it's really not amplifying. It's only giving you unity gain from input to output. However, the feature of this amplifier is that we have a very low output resistance. If you remember, when we looked at amplifier case, if you have a chain of amplifiers, then we would like this is the equivalent circuit of the amplifier, AV times VI, and here is your R out, and this is your RL. If you remember the examples we did of cascading of amplifiers, then you might remember that if you have a small RL and if R out is substantial, then you have a voltage divider effect over here between the two resistors. Even though you have a large gain AV, it will get reduced because of the voltage divider effect. So our desire is to have R out as small as possible. In general, what you do then is you may have a chain of amplifiers amplifying the signal, and the last amplifier needs to deliver your signal to a, let's say, small resistance. For example, in the previous case, we had explained if I am driving a speaker. So speaker has a 8 ohm resistance or something like that. Then I can use common collector or emitter follower amplifier over here so that I can make my output resistance R out of that amplifier to be really small by increasing the current I flowing through the transistor, and then I can still get reasonable gain. We are going to go through one numerical example based on this. One last thing we will do in this lecture is figure out what is the effect of this low resistance RL on our common emitter amplifier. So from AC point of view, our amplifier will look like this. I would like you to first go through the KCL KVL for this schematic. So in this case, what we are trying to do is effect of RL on emitter follower. So KCL at the emitter node will give us So one quick trick I'm going to show you is sometimes we have conductance and resistance in the same equation, and it becomes a little bit cumbersome to handle it. Now in this particular case, you can see that I have a transconductance GM, however I have resistance over here. So the equation would become a lot easier if I would just do a R to G transform. So I like to use this trick to get a quick answer, and at the end I would substitute things back. So the transformation is GL is equal to reciprocal of RL and G pi is equal to reciprocal of R pi. If you practice it a couple of times, then you can solve complex equations very quickly. So our equation becomes GL times V out is equal to G pi times V in minus V out plus GM V in minus V out. So rearranging, we would get GL plus G pi plus GM times V out is equal to G pi plus GM times V in. So V out divided by V in, which is the gain we were looking for, would be G pi plus GM divided by GL plus G pi plus GM. Now we can undo our transform. This should give us reciprocal of R pi plus GM divided by reciprocal of RL plus reciprocal of R pi plus GM. Now what is the insight over here? If RL was infinity, then the gain would be 1. And in this case, the gain would be close to 1. However, it will be always less than 1. Okay, always less than 1. So emitter follower gives us gain which is less than 1. In the next lecture, we'll pick up from this point.